let's just start off with, I'm assuming you've got your books open already. Can you please write down the general form of a linear equation? Linear equation. Oh man, you're either going to like this or hate this. Okay, look, the only reason why you wouldn't have done it by now, there's two reasons. Number one, you're too slow getting your books out, or number two, you've forgotten. The general form of the linear equation, of course, is y equals mx plus c.
M and C.
I don't care if
Can
you
you do AX plus B?
I don't care if you use AX plus B. It's not usual for Australia to do that. Your calculator might do it, and some American text might do it, but we would normally use MX plus C. Okay, that's it. Thanks very much. Have a good holiday, everybody.
Suits me.
All right. Write this down for me. F of x equals mx. No. This is going to be the same linear equation form. What would I put instead of c using function notation? What is c?
The y.
It is the y-intercept. Good.
Zero.
Stop. Think. Write down. Because the problem. Thank you for sharing. I apologise for making you stop then, but I wanted everyone to think and write down something. What is c? Parav has already started you off, and I shut you down. Parav started off by saying it's the y-intercept, remember. So what is that in function notation? Don't say it out loud. It's not. No, it's not. C is not a function notation. C is a letter which represents the y-intercept.
Oh.
What is it in function notation? I will call on you in a second, I promise. Lovely enthusiasm. Okay, alright, go.
F of 0.
F of 0. Good. Okay, I'll be here. So it's F of 0. Okay. Next bit, what about M? See if you can write it down in function notation. Honestly, if you get this, I wish I had little chocolates to hand out as prizes. Can you write M in function notation? Hello? Oh, I thought we were going to have visitors. While I'm thinking of it, by the way, good to have you in the video. Next term, we're going to have a room shift. Sadly, it's still a science lab, but we're shifting to C110.
Is that the physics one?
Yeah. Was it worse, is it? I haven't even been in there. The good news, though, is that I think we'll have all 3 lessons in that one room. Don't have to shift between rooms.
Is it F of 1?
No, because that would just be the value of y when x equals 1.
And then it's the value of
No.
Why?
Because m is the gradient. It's not the value of the function that.
Yeah, but that's linear. So like at 1, the curve that's exactly the value of n.
But m is a rate of change. If you said f of 1 minus f of 0 over, then that would be okay. But it's not. Well, it's not.
So it's a gradient.
Sorry? F of 0 is not necessarily.
M is a gradient.
Yep.
So M is equal to y2 minus y1.
So
Divided by x2 minus x1.
Yeah.
Is that it?
So how is that suddenly f of 1? Let's work it out, because this is not where I wanted to go, but I like your thinking anyway. So what is m? So m could be seen as y2 minus y1 over x2 minus x1. That's true. We could also, because that's true for any pair of values, we could choose x2 to be 1 and y1, x1 to be 0, and that'll give us over 1, which would just be the top number. But where you went wrong is you said that would be just f of 1. It wouldn't be. It would be f of 1 minus f of 0. F of 0 is not 0. It's whatever value y is when x equals 0. And so you would end up with f of 1 or f of 0. Sorry, minus f of 0. Great, does that make sense?
Yeah.
Yeah. So you're on the right track, but you weren't quite there. And you made a fairly common mistake of saying, well, f of 0 must be 0 kind of thing. When you think about it, it's not. It could be, but it's not. So it is true that you could write this now as f of 1 minus f of 0 plus f of 0. Yeah. X, sorry. It's really important. Let me rewrite the whole thing. Not the whole thing, just up to there. So you could do that. Not what I was aiming for though. Anyone has something different? Doesn't make it bad, just makes it not what I was aiming for. Yep. Sorry?
Derivative.
Yeah, which is what? How would you say that?
Let's put f dash.
Yes, f dash of x.
Oh my god.
Or dy over dx.
Oh my god. That was so much simpler than we.
Yeah.
In front of me.
So I told you this would kind of break you a little bit. My point was really this. My point is that the derivative of the function will give you the gradient, and so that actually forms part of a linear function in regard. Now, that's not too mind-blowing once it's put in front of you, I think. Can we do a similar sort of thing here? Maybe we could also do it from this format too, couldn't we? I won't necessarily get you to do it, but we could sort of do a similar thing here. So sorry. I'm having just a bit of a bad day for some reason, and I just keep on. My brain's scrambled. I think it's just the end of term. So y minus y1 equals n outside of x minus x1. You know that format? You know? So we could also do something similar to that, in that we could let's just pick a point, x1. We could say so we could transform this to f of x minus f of x1 for some point is equal to f dash of x outside of x minus x1. So what I've really done is I've kind of just put it all in terms of f and x1 kind of thing. There's method to my madness here, trust me. Okay, so let's have a look at, everyone, can you please fire up Desmos? I'm going to make this up as I go along a bit, so see how I go. Desmos. Can you put in this graph? I'll turn it off so you can't see it. No, that'll do. I think this will be okay. I'm sorry if I'm making things more complicated. I'll say that in advance. But just put in f of x equals 1 on x. And again, I'm not going to, at this point, go through, I'm not going to go through the technical why this graph looks like it does. It's called a reciprocal function, 1 on x. So if you've done that, you'll get this. Hooray! Now you can go home. No, you can't. Okay, so we've got this. It's called a reciprocal function. It's pretty. It's got an axis of symmetry that's diagonal. So this bit is reflected across here to this bit, which kind of reminds me a little bit of inverse functions. You know how they're symmetrical across the diagonal? A little bit. We can also work out the derivative of this function. Do that in your paper now, on paper now. Your time starts now.
It's on the video.
Done it? If you haven't done it yet, you're not fluent yet with derivatives. Practice more, please. This is a pretty straightforward derivative. Sorry, I don't mean to be rude, but it is. The good news is, if you haven't got it yet, it's just practice. Just for the notes, I'm just going to put it a little bit more formality. Now consider f of x is equal to 1 on x. Then f dash of x is equal to...
Minus 1x minus.
Hang on, I better put it here as well. So if you put it in negative index form, so 1 on x is x to negative 1. So that would be minus 1 x to the negative 2, which equals minus 1 on x squared. Okay? If you didn't get that, please practice it until you're solid with it. This is a derivative. What does that derivative mean again?
The rate of change.
Thank you. At any point on the graph. So if we go back to Desmos, we will see that the rate of change is different at every single point along here. But it is just a rate of change. Yes? It's just a rate of change. Which means that that value could also be the rate of change for a different graph. Okay, it's just a different point. So what we're going to do is we're going to explore this in linear graphs. So we're going to find a linear graph which has the same rate of change at a particular point. So let's start off with, let me see now, what would be slightly interesting? Looks like x equals 1. So what would f of 1, so f of 1 is equal to 1. Yep. Let's have, Desmos is good for this. If I go f dash of 1, it'll tell me what the gradient is. Negative 1. Does that make sense for what we calculated? Negative 1 on 1 squared is 1 on 1, which is 1, negative 1. Okay, so that makes sense, yes? Okay, so it has a gradient of f dash of 1. Now let's form a linear equation with the same gradient. Let's make c equal to 0 to start with. Y is equal to f dash of 1. See how I'm using function notation instead of m? X plus c. Good so far?
So that's working off what you've already put in.
So if I change this to a half, say for example, we can see that the gradient will be minus 4. So if I make this one 0.5 as well, we can see that it's tough. And it kind of looks like it might be a steeper point there as well. So it kind of makes sense that this is mirroring what's happening at that point. Good so far? Okay. Using these numbers here is a little bit annoying because I have to keep on changing them. So instead I'm going to delete the numbers and just put A and add a slider. I expect you to be doing the same. And then I can replace this with A as well. Okay, so A has started off as 1. So the gradient there is the same as the gradient there. And as I move, we can see it's getting flatter or steeper or changing direction. Good so far? Yay. Now, the last thing we're going to do is we're now going to make the linear graph and the function f of x, we're going to make them intersect. Now, remember, intersect means it shares a common point. Okay? So I'm going to go back to the notes. This might be getting a bit too tricky, so just bear with me if your mind is already blown. We could use this kind of notation to possibly find the point of intersection here. Okay? We could use this kind of notation to see whether we can shift this graph so that it's on the graph instead of just in the middle like so. I'm going to pause the video and give you a couple of minutes to think about it. It might be a bit too tricky. Okay, so resuming. First of all, I was pretty unclear before, all my fault. Of course, you could find a value, any old value, to add on as c to the y, the linear equation, and it would intersect with the graph. Of course, it would do. Arrow, for example, you just change the gradient to negative, and then it flips it and cuts it in 2 places. Exactly what I asked to do, but I didn't articulate well what I wanted. And what I really wanted is to know what it would be like if we moved the linear equation so that it shared the same point on the graph that we had worked out the gradient. So we're looking at a equals 1, so that's f of 1. So there's f of 1 there. The gradient at f of 1 is equal to -1. And so the function would be y equals f dash of 1, so the same gradient, but also by putting this bit in here, f of a, that's the y coordinate, and a, which is the x coordinate, I'm actually getting it to share the same point as well. Specifically, the point where I had that gradient, as opposed to any old thing. Okay?
And then if you move A, does it stay?
Yeah, so there's a couple of things I wanted to show you. Number one, this point on the graph, its instantaneous rate of change is -1. It's also the rate of change of this linear graph. And we know that for a linear graph, it's the constant rate of change. But the thing I wanted to really point out here is that if I zoom up more and more and more and more, can you see that it is in fact touching that graph and then moving on from it again? So when you have a line that approaches a graph at a particular point and then keeps moving on, as opposed to just cutting through the graph, it's called a tangent line. So this is a tangent. And Lily asked a question, what happens if we change the value of A? And you'll see rather nicely that the line rolls around the graph, like so. Okay? So it rolls around the graph. So that is the nature of a tangential graph. So what does that mean? One of the skills that you need to learn is to be able to work out the tangent, because as you've seen from the video work, effectively the tangent line is the linear equivalent of what's happening at that rate of change. Okay, so it's kind of almost like an average rate of change at that point. So being able to come up with a linear function, as a simple example, if you're talking about physics, you may have a function which describes some sort of a force function of some sort. Then this would be the linear force required at that point. Yeah, a tangent. Tangential line, but a tangent or tangent line. So tangent. So coming up with the tangent is kind of important for lots of different parts of science, physical sciences, because it does mirror the behaviour of the graph at that point as a straight line. Okay, and you can see that from the way it rolls around the graph. So how do we work that out? I got you to do all that hard work there because I wanted you to see that effectively to work out this tangential line, we just need to be able to determine the gradient at that point and then use the coordinate of the original function to come up with our linear function. And that's basically it. And then we can transform this into general form if we want to. But yeah. Okay. Now there's a related concept called a normal. And a normal is a perpendicular line. So let's see if I can get this going quickly. It's going to be at the same point, so y minus f of a equals m times x minus a. So that would be for any old gradient. Okay, you can see it's passing through there. But we want to make sure it's a bad choice, hang on. But what makes a normal is that it is at right angles to the tangent. Can you remember from our linear work what conditions we need for one line to be perpendicular to the other in terms of their gradient? That was about 4 different responses, which I think were the same response, more or less. And that was, m1, m2 equals -1. I heard a -1, I heard an m. But the other way of looking at it, do you remember what I said? The other way of looking at it is saying -1 over. Yeah, -1 over. So what I'm going to do here is I'm going to make the gradient -1 over f dash of a. Don't need that bracket. And can you see that it pretty much looks right angles there? Might just change the colour so that you can see a bit better. Yeah. Okay. So as I now slide A around, it's staying as a right angle, the green line. So the blue line is tangential and the green line is a normal at that point. So if you were trying to, like if this was, I'm not very good at coming up with physical examples because my physics is quite weak. But if this was the trajectory of a ball or something like that, and you needed to knock it straight on, then this function would tell you the exact perpendicular force that would be required here. Okay, so tangential or tangent and normal, perpendicular to the tangent. Okay, so that's the theory behind what we're doing. Let's have a look at the practice. So I'm going to make up this example as I go along and just hope it works out okay. So this is an example of how to do tangents and normals. But f of x equal to x cubed on 3. Find 1, equation of the tangent at x equal to 3, and 2, equation of the normal at x equals at x equals 6. See how that goes? I'm worried about the size of the numbers there, but give it a crack. So, 1. F of 3 is equal to 3 cubed over 3, which is equal to 9. So the point is 3, 9. Good so far? This is going to be the point that the tangent's going to have in common. F dash of 3, f dash of x is equal to 3x squared on 3, which is equal to x squared. Therefore, f dash of 3 is equal to 9. That's going to be the gradient. Question? Ready?
No. No.
All good? Any questions from anyone else? Okay. Therefore, tangent is y minus 9 equals 9 outside of x minus 3. I'll colour code this. 3, 3, 9, 9, 9, 9. That last bit made me feel like I was being very negative in German, but still. Can you see? Again, because I'm making it up as I go along, I've now got dumb things like the gradient is the same value, just happens to be the same value as the y coordinate. That's just a coincidence. Because your teacher's a bit slow today. Whoever just said what else is new, that's rude. Okay, so, good? No one said that. You know what? You've just found the tangent equation. That is a legitimate form of the tangent equation, but let's put it into mx plus c form because we're brilliant. I'll give you 30-second head start. Put it into y equals mx plus c form. If you prefer to put it into y equals ax plus b form, go for it because it's the same form. If you can't put it into y equals mx plus c form from this, then what you need to revise is your basic algebra skills. Expand the right-hand side. Add 9 to both sides. Done. Again, optional. However, in a test, you might be asked to put it in general form. Questions? Normal is not much more difficult. It's just one extra step. So, f of 6 is equal to, really wish I hadn't done this, 6 cubed on 3. Can someone tell me? 6 squared is 36 multiplied by 2, 72. Doesn't feel right. What is it?
It's
6 times 6 squared. 3 goes to 6 twice. 6 squared is, I'm still thinking 72. 72, cool. 72. Again, just really quickly, I just split 6 cubed to 6 times 6 squared. 6 divided by 3 is 2. 2 times 6 squared is 2 times 36, which is 72. That's just how we roll. Okay, 6 comma 72. F dash of x, f dash of x we've already worked out, but let's just do it again for funsies, is equal to 3x squared on 3, which is equal to x squared. Therefore, f dash of 6 is going to be 6 squared, which is equal to 36. That is the gradient. Shall I squishy into this one? Therefore, normal is m equals negative 1 on 36. Yeah? 36 times m equals negative 1, etc. That's how you do it. I'm not going to be able to squish it enough. Therefore, y minus 72 is equal to minus 1/36 of x minus 6. And I won't, because of room, I won't put it into general form, but that's basically the equation of the normal. What do you think, guys? The rest is rinse and repeat. You'll be given different functions. You don't even have to know how to graph them, but switcheroo to Desmos. And if I put in the function first, y equals x cubed on 3, divided by 3, that's what it looks like. Oops, divided by 3, that's what it looks like. If I now go, what was it? The tangent at 3, we would have y equals 9x minus 18. And that was at the point x equals 3. It's all the way up here, but can you see it's sort of basically up there somewhere? So a nice tangential line. And then the other one, which we're going to have to zoom way out for, is y minus 72 equals, thank you, equals negative 1 on 36 multiplied by x minus 6, close brackets. And I'll have to zoom out a fair bit for this. Return. Where is it? Oh, there it is. Can you sort of see it's... Ignore the blue line now. That's kind of right angles there.
Kind of.
I mean, it's right angles at that point. It's not right angles slightly after or slightly after or slightly before. But at that point, it is a normal. It is perpendicular to the graph right at that point.
Surely it has to be afterwards as well, because otherwise it's going to be
What do you mean afterwards?
like further up or down the line.
No, not for this particular equation. It's exactly perpendicular here. But if I then translated this up a bit, the thing is it's going to be difficult for you to see it. It's not perpendicular at that point. It's actually might be 89 degrees or something like that.
Yeah, but if you leave the line where it was before without the +2, it's still further up and down the line. You can still make a right angle.
Oh, up or down the green line? Yeah.
Like,
you mean draw a bigger box?
Yeah.
I get, yeah. But it is at right angles at that point. Okay? The two lines are at right angles at that point. Okay, does that make sense? Practice time. We've got 10 minutes. Here, you've got, so what you did yesterday was you practiced 5C and 5D. Now tangents and normals, which is 5E and 5F. They are all of good value, but you can go into them and either do every single one. If you think the early ones are easy, then you can move on to the harder ones, but see how you go. I know it's only 10 minutes, but the explore was important. So we'll start next the first lesson next after the holidays, looking at this in more detail. But 5E deals with tangents, 5F looks at normals. See if you can do at least one from each exercise before you leave today to consolidate it.